Alright guys, here we go with an explanation of example 2. Basically it's the same idea, except we've got a rational function now and not a polynomial, and we don't have all the steps laid out. So I'm just going to make some numbers here and go through all our steps. So step 1, I'll turn the music down a little bit. Step 1 was to do domain range. Okay, I believe. Yeah, and that's going to include really step 2 also, which is discontinuity. So the domain for this thing is going to be all reals except x can't be 0, right? And actually that means we have a vertical asymptote, not a hole at x equals 0. So I'm just going to draw that in right now while I'm thinking about it, while I'm remembering. And if we think about our sort of other properties of rational functions, we've got a higher degree term in the bottom and the top. So that is telling me, oops, let me go to black here. That's telling me that we've got a horizontal asymptote also at y equals 0. Okay, so again, that doesn't necessarily mean that this asymptote doesn't get crossed. It might, but it guides our end behavior. Okay? Yeah, so I think that's it for steps 1 and 2. Yeah, step 3 is end behavior. Okay. So if I want to write out these limits, we don't necessarily have to. But just a good habit to get into, right? And it's a rainy day anyway, so why not kind of do this thoroughly, right? I'm going to leave it till later to see if we can put a plus or minus on here and describe more explicitly the specific end behavior. Okay. I think step 4, if I remember right, is easy points. Yeah, and then we go to derivatives. Okay. So there is no y-intercept here because, again, we have x can't be 0, right? Because this x cubed here. Can 7x squared minus 7 be equal to 0? Absolutely. If x is 1 or negative 1, 7 times 1 minus 7 is going to be 0. Okay? So we do have x-intercepts at plus or minus 1, 0. I don't really need to write the whole point, but I could have just write at plus or minus 1 because I'm indicating x-intercepts, but might as well put that in there. I'm not going to erase it. So in fact, yeah, we've got 2 places here where this horizontal asymptote is going to get touched. Okay? So, well, this is kind of done. I haven't put the plus or minus on yet. Okay, 5th. Now this is first derivative stuff. Okay? First derivative stuff. Just a little bothered by how I wrote that 5. Okay, so let's make this a little bit bigger. So f prime of x, I'm going to use quotient rule. F prime of x is equal to low d high. Well, the low function is x cubed, excuse me. D high is 14x minus high 7x squared minus 7 times d low, the derivative of the low is 3x squared, all over low squared, which is x to the 6th. Okay, if we clean this up, let's see. It looks like an x squared can come out of everything, and that's going to leave 14x squared here. Okay, if an x squared comes out here, I have x times 14x is 14x squared. This x squared has come out. Actually, I should have taken the 7 out too. Yeah, let me do that, guys. let me do that. Okay, so I'm going to take, just erase all this. Sorry. So let's take a 7x squared out. Okay, and what that will do, now that will just leave us with 2x there. And then we'll have minus, the 7's come out, and I've got x squared minus 1 times 3x, right? Because this x squared has been taken out. Because this is all multiplied together. So this 7 was taken out. This x squared was taken out. All over x to the 6th. Okay? So now if we clean this up a little bit, this is going to be 7. I'm going to cancel the x squared and the x to the 6th. And we've got 2x minus 3x cubed plus 3x. And yeah, you guys probably saw this. I caught another one of my errors. I was wondering what was going on. If we took an x squared out here, this x squared should be gone. So it should not be 3x here, it should just be 3. Okay? So, sorry if you guys saw that before I did. And that means that our second kind of part of this numerator here is just going to be, that's more like we want it. That's going to be 3x squared plus 3, okay? And so hopefully that'll factor. And then this now is x to the 4th. Okay, one more cleanup. So this is the same thing as 7. I'm going to write this over here. I'm going to take a negative out. So it's going to be 3x squared minus 2x minus 3. Is that going to factor? 3x, x. Yeah, I think it will, right? Plus 1. No, it won't. That's annoying. Don't think it will. That's 3, yeah. Okay. Well, let me just write it like this for now. I might take another look because I don't know if I'm totally confident in that. Hate to say, but okay. And just out of curiosity too, I'm going to check the discriminant of this. So b squared minus, I'll do it over here. But I want to see if this has zeros, right? Let's do it over here. B squared minus 4ac. That's going to be 2 squared, negative 2 squared is 4 minus 4 times 3 times negative 3. Okay, it definitely is going to have zeros. Yeah. Let me just check these notes, guys. Okay, apparently I've made a error with my derivative. Okay. Let's check this one more time. I apologize for this, but maybe you can skip ahead if you've already seen my mistake. All right, let's check the derivative again. Low d high, that's right, minus high d low, all over low squared. Okay, so 7x squared. Right. And this is that's 2x squared. Ah, come on, Jeff. That's pretty bad. So 2x squared 2x squared. And then that makes things a little bit easier, right? So we get 3 minus x squared in our numerator here. Okay. So let's recopy this. This is still a 7. And now that's just 3 minus x squared. Okay. And that is a lot easier. All right. Trim this. And now what we want to do is kind of make our number line for f prime. So I'm going to do that. I'm going to do that here. All right. So f prime of x, and we've got 0 to worry about because number one, it's a vertical asymptote, and it's also something that is create a critical value in the first derivative, and then we also have plus or minus root 3. Okay, so I'm going to make 3 kind of tick marks here. And then we can just go with checking numbers. Let's see, if x is 2, a number bigger than root 3, this will be negative, right? Because this is going to be bigger than 3. So the whole thing will be negative. That's also going to be the case if x is like negative 2 or anything less than negative root 3. So these will both be negative. Okay. In between root 3 and 3, like if I pick 1 or negative 1, this will still stay positive, this will stay positive, this will stay positive. So the whole thing is positive. So our sign chart here goes negative, positive, positive, negative. Now I'm not going to write the increasing or decreasing part because I want to save some time, and we're really just asked to go do the graph, but this means decreasing, increasing, increasing, decreasing. Okay? And we have the 3 important x values. All right, second derivative. So second derivative, which I believe is step 6. Actually, it might be 7. Let me check because I think 6 was, yeah, maxes and mins. So we'll do those first, yeah, and then second derivative, then point inflections. Okay, so we know that at excuse me, at 0 it's undefined, but we have a relative min here and we have a relative max here. Okay, so let's say that we've got a relative min at the x value is negative root 3. We're gonna have to compute the y value. And the relative max is at positive root 3, and we'll have to compute the y value. Okay, so if we take negative root 3 and plug in, really we need a calculator for this, right? Because this part we could do. This is going to be 7 times 9, right? Excuse me, 7 times 3, which is 21, minus 7 is 14. This is going to be 3 root 3, negative. So we'll get negative 14 over 3 root 3. Okay, and if we have a positive, it's going to be same numbers, but this will be positive. So this will be 7 times 3 is 21 minus 7, which is positive 14 over positive 3 root 3. Okay, 14 over positive 3 root 3. Now I'm just going to cheat and kind of look at these decimal values that we got. Here we go. I didn't give them. Okay, so let me just compute those real quick. 14 over 3 Sorry, here the Inspire's firing up. So this is a little bit ironic because we have to have the calculator to get these exact decimal values. That's okay though. Okay, so 14 divided by 3. 3 root 3. And the Inspire is saying that's about let's say 2.7 roughly, right? So these are roughly, this is negative 2.7 and this is positive 2.7 roughly. Okay. So yeah, let's plot those now. So negative root 3 is somewhere between negative 1 and 2. So I'm gonna go like, I don't know, maybe here. And negative 2.7 somewhere there. So I'm gonna roughly plot that point, right? And we'll label it later. And then we have the positive version of that, like somewhere right about there. Okay? So that's first derivative analysis. Compute the first derivative, got the form we wanted, got the number line, and got the relative mins and maxes. All right, almost done, guys. Just need to do second derivative and analyze that. So second derivative, f double prime of x. Well, let's use this, right? So another quotient rule, low d high, so that's x to the 4th, and then the derivative of the high is going to be negative 14x. Okay, low d high minus high, so that's 7, hope I have enough room, 3 minus x squared. High d low, that's 4x cubed. Okay, got it all in. And then all over low squared, so that's x to the 4th square, which is x to the 8th. All right, let's see if I can not bungle the factoring here. Okay, so a 7 can come out. That's common to both. And then an x cubed can come out, because that's common to both. Okay, if we do that, be very deliberate here. I've got an x here. I've got an x here, so I've got x squared left, and I've got a negative 2. So that's going to be negative 2x. All right, let me just double check that. Negative 14x to the 5th, negative 14x, see, almost did it again. It's negative 2x squared. And then if the 7 comes out of the second part, this is gone. Well, let's do this. Let me take this negative out too. Okay? And hopefully I won't bungle that. That means this is a 2x squared. Okay? This negative is gone. This 7 is gone. This x cubed is gone. So I have plus 3 minus x squared times 4. Plus 3 minus x squared times 4. And that looks good. All over x to the 8th. Now, we'll clean it up a little bit. That's equal to negative 7 times 12 minus 2x squared over x to the 5th. Or, geez, one more. I know, I think it's negative 14 times 6 minus x squared. Whoops. 6 minus x squared. Let's try that a third time. 6 minus x squared all over x to the 5th. Yeah. Okay. So with our second derivative now, I'm going to make it a little bit lengthier because we have bigger numbers here. The 0 is still in there. And now we have plus or minus root 6. So I'm going to put that like out here. This is negative root 6. And maybe here is positive root 6. And this is f double prime of x. Okay, so now if we pick some test values, well, if x is between negative root 6 and positive root 6, this part will be positive. Well, geez, it matters if it's positive or negative because of this. Okay, so if x is between 0 and positive root 6, this is positive, this is positive, this is negative. So the whole thing will be negative. If x is between 0 and negative root 6, like for example negative 1, negative, positive, negative. Negative over negative is a positive. So this is positive. And if x is bigger than root 6, negative, negative, positive. So whole thing positive. And finally, if x is less than negative root 6, negative, negative, so positive over negative. Positive over negative is negative. Okay. Wow. So we also have important values at negative root 6 and positive root 6, because those are going to be places where we have points of inflection, right? The concavity changes. Okay, so that I guess would be step 8. I'll write that here, right? So we're just kind of going this way. POI is at root 6. Compute the value in a second. Negative root 6. Compute the value in a second. Yeah, so we want to evaluate this function here at positive root 6. So I'm actually going to use Desmos this time and graph it. I think that's going to be easier. So bear with me while I'm doing that, or you could kind of calculate yourself, see if you agree. So let's put this graph in. 7x squared minus 7 over x cubed. Okay, so that's the graph, and now I want to look at an intersection at root 6. Okay, so that's Desmos is giving me about 2.4. So this is, I know this is, this isn't calculus part, guys, so I'm being lazy here. This is about 2.4. I'm going to say via Desmos. And the other one, I believe, will just be negative 2.4. Yeah, and it is, roughly. Okay. Yeah. So now we can plot those. So root 6 is, somewhere between 2 and 3. So if I'm going to plot this point, I'm going to go a little bit to the right of 2, and I'm going to go up 2.4 units. So 2.4 I'll say is like right there. And then negative 2. 2.4 I'll say is like right about here. Okay? All right. So if we look now at sort of our parts, right? Graph is decreasing. When x is less than negative root 3, which is right here. So the graph's going to be decreasing, right? And if you notice, it's concave down, which means it's going to be spilling water, until this point, which is root 6. Then it goes concave up. Okay? It stays concave up and starts increasing. So I'm going to try and graph that first part, right? And I got to adjust sort of how I'm holding this thing. So concave down, hopefully. A change right there to concave up. It's really hard for me to graph that cleanly. Let me try that again. Maybe I'll try it this way. Let's make that concave up, and then that goes concave down. Yeah, that looks a little bit better. And then, well, I've got it increasing just a little too early, right? You guys can see. So it's decreasing, concave up, flattens out, and then steeply is increasing. Okay? Now we're at the x-intercept, right? This thing's going to continue increasing, right? All the way until positive root 3. Right? And we've got this asymptote here. So basically, I just need to keep this thing looking increasing and concave up all the way. Okay? It crosses over the vertical asymptote. And now we're to the right of 0, so it's still increasing, but now there's been a change in concavity. It's concave down, okay? And it will remain concave down until we get to root 6, which is this point. So basically it's gonna almost, you could think of it as looking like some sort of parabola, right? And again, maybe it's easier if I start at this point. This has got to be concave down, right? So it's got to be like that. You guys are probably saying Papa Duke is taking way too long to get this right, but I don't know. I want to get it right. So let's try it like this. All right, something like that. Sure, close enough. Okay, close enough. And at root 6, which is right here, well, what happens? The thing is still decreasing, but now it's changed to concave up, right? So it's going to have a point of inflection. It's going to look almost like a parabola opening upward. Okay, so that means it'll do one of these. It's looking like it's going to hold water there. All right, I know I should just let it go, but I can't. I just got to get this part right. Right? Just got to get this part right. Okay, now I finally will accept it. All right? So, there's the graph, guys, right? That's our relative max. We've done everything now. So we got the points of inflection, and step 9. Step 9 was the curve sketch. So I'll just put that right here. That this was our step 9. Okay. And if we wanted to, we could label all these points that we calculated from either the original function or the first derivative or the second derivative, but I won't. I guess I'll just highlight them. So we had the x-intercepts, right? Which are right here. We had our relative maxes and mins, which, let's do a different color for those. We're right here. Don't want to box them out. I want to be able to see them. Okay, so there's our exact and then approximated values. So those were, there's the relative max and there's the relative min. And then finally we had our points of inflection. Let's do like a green for that. Okay. So you're welcome for extending this video for about 5 minutes longer than I really needed to. Hope you guys bared with me, right? But this is very specific, okay? But I just think it's pretty cool that, you know, we can make these really accurate looking graphs without use of a calculator. The only time we used the calculator was to get, you know, an approximation for how low these values were and how low these values were. All right, so I'll stop the video now, and yeah, hopefully these were helpful.